This is a review of solution math using the quizzes that we teachers at Johnson High School assigned our students to do in distance learning. And we're not going to go over all the problems, just those that more than 10% of students did not get correct. So question 2 asks, when the volume of a solvent increases, the solubility of a solute at a given temperature does what? Well, solubility is defined, if you recall, as the mass of solute dissolving in 100 milliliters of water. Stop and think, is that an intensive property or an extensive property? If you need to think about it or look it up, turn the video off and then come back. Well, this is an intensive property. If it's intensive, it stays the same no matter how much volume is tested. So it's just like density of, say, water. So the solubility at a given temperature is fixed. And so it's going to stay the same. All right, number 3 asks, in general, as the temperature decreases, what happens to the solubility of the substance? And remind us that solubility is the mass of a solute that dissolves in 100 milliliters of water. So what happens to the energy? This is easier to think about. The energy of the surrounding water molecules as the temperature increases. Well, if it increases, the energy of the surrounding molecules will increase because temperature is a measure of kinetic energy. Therefore, the molecules are hitting the solid harder and more frequently, and more solid will be kicked into solution. The water is going to be able to get between the solid particles more easily, and the solubility will increase. Now, this is just exactly the opposite for gases, because gases are, of course, not condensed phases of matter. And when they get hit with energy, they're going to get out of the solution. So, let's now look at the situation with the solid dissolving in water. If the water molecules then have less energy, the solubility can't increase, it has to decrease. So we have an unsaturated solution, and there's how you make it. And how do you make it saturated? Well, solubility is the mass of solute in a saturated solution. You can't put any more of the solid in. If the solution's unsaturated, then can it take more solute? Ask and answer the question. Well, yes, it can take more solute, so you saturate it by adding more solute. In this case, you add potassium nitrate. All right, question 6. Calculate the molarity of a solution containing 1.5 moles of sodium chloride in 0.50 liters of solution. Molarity is the concentration. It's the number of moles of solute in a liter of solution. Or it could be the millimoles of solute in a milliliter of solution. And that is how we write that. Molarity, with a capital M, is moles of sodium chloride in this case, in liters of solution. Well, we have 1.5 moles of NaCl and 0.5 liters of solution. When we do the math, we see 3.0 moles per liter, and that's symbolized with a capital M. How many moles of sodium chloride are present in a solution with a molarity of 8.59 molar and 125 milliliters of the solution? Well, we go back to our definition of molarity, and we're given the molarity here. So to find the moles of sodium chloride, we would multiply both sides of the equation by the volume, liters, and we get moles of sodium chloride equals moles of NaCl divided by liters of solution, that's the molarity, times liters. Now let me point this out. If you just put a capital M here, you wouldn't be able to see that liters of solution over liters of solution is 1. And you perhaps wouldn't realize why moles comes out of this calculation. So I always recommend when you do a calculation involving that capital M, change it to moles over liters or millimoles over milliliters. So we multiply the molarity times the volume, and we get whether it's millimoles or moles. And here we get question mark millimoles is 8.59. There's your capital M translated times 125 milliliters. That's 1,070 millimoles, or 1.07 moles. Question 8. The molarity of a solution with 224.1 milligrams of sodium chloride in 50.0 milliliters of solution. We are not given millimoles, we are given milligrams. There's our definition of molarity, and we know that a mole of sodium chloride gives us a mole of sodium ions and a mole of chloride ions, and therefore we add the molar masses of the sodium and chloride atoms or ions, and it's 58.44 grams per mole, or 58.44 milligrams in a millimole. So, how many millimoles of sodium chloride do we have? We have the 224.1 milligrams, and we're going to divide by 58.44 milligrams per millimole, and we get 3.835 millimoles. 4 sig digs all the way through here. We then divide by 50.0 milliliters, 3 sig digs, to get the molarity in millimoles per milliliters, and we have 0.767 millimoles per milliliter. Moving to number 9, how many moles of solute are needed to make 2.5 liters of a 0.38 molar solution? Well, from our definition, we found a couple of slides ago that moles of solute equal liters of solution times molarity. So we multiply 2.5 liters of solution times 0.38. See how I did this? Instead of putting a capital M, I wrote down what it meant so that I could see liters over liters as 1. And we end up with 0.95 moles of the solute. If we were asked for how many grams of solute, we just multiply by the molar mass of that particular solute. Number 11. Again, these are questions that a lot of people missed. We're starting to get a little more complicated. So we have 360 milligrams of aspirin, and we give you the molar mass. That's helpful. And we're going to dissolve that to produce 200 milliliters of solution, and with the molarity of aspirin in a 50 milliliter sample. Now think, is the molarity going to be different in the 50 milliliter sample of the solution than it is in the 200 milliliter sample of solution? And I think you'll realize the answer is no. The molarities are going to be the same. So there is our equation that we've been using. So the millimoles of aspirin would be 360 milligrams, and we're going to divide by 180 grams, should be milligrams per millimole, to get 2.00 millimoles, and we then have 2 divided by 200 is 0.01 molar, 3 sig digs. And this is true no matter what amount of solution is considered, the 200 milliliters or the 50 or 5. The molarity is going to be the same because the solution is uniform, homogeneous. Number 12. This caused a lot of trouble for quite a few students. So we've got 40 milliliters of 0.25 molar KOH and 60 milliliters of 0.15 molar BaOH2. What's the molar concentration of hydroxide in the resulting solution? You're going to be working with barium hydroxide in second-year chemistry, so you ought to get used to this. We're assuming then that the total volume is 60 plus 40. So there's your molarity. So millimoles of KOH would be 40 times the 0.25 molar, or 10 millimoles. The barium hydroxide molarity itself is 60 times 0.15, or 9 millimoles. But since barium hydroxide has, we say it's dibasic, it has 2 moles of hydroxide in every mole of the base of the barium hydroxide, we have to multiply the 9 millimoles of barium hydroxide by 2 millimoles of hydroxide per millimole of barium hydroxide. Now we got 18 millimoles of hydroxide. So the hydroxide total is the 10 here from the KOH plus the 18 from the BaOH taken twice. 28 divided by 100 is 0.28 molar. Number 13, any salt that dissolves in water breaks up entirely into ions. So how many millimoles of sodium ions are in 100 milliliters of 0.1 molar sodium phosphate? Look at that formula. Well, there's your concentration formula, and the millimoles of sodium phosphate is volume times molarity, 10 millimoles. But each mole of sodium phosphate breaks up and gives you 3 millimoles of sodium ions. So the millimoles of sodium ions is 10 millimoles of the salt times 3 millimoles of sodium ions per millimole of salt, or 30 millimoles of the sodium ions. Question 14, how many grams of calcium chloride would need to prepare 100 milliliters of 0.1 molar chloride ions? There's your solution, again, your mathematical formula, and we're going to just multiply the volume times the molarity to get 10 millimoles of chloride. But each chloride is from a CaCl2, and there's 2 chlorides for every CaCl2. Therefore, we have to multiply the 10 millimoles of chloride by 0.5 millimoles of salt, gives us 1 millimoles of chloride ions, 5 millimoles. We then multiply by the 111 milligrams per millimole to get 555 milligrams, or 0.555 grams. Finally, number 15, I give you the breakup, the dissociation formula here for aluminum nitrate, and they tell you that the concentration of nitrate is 0.10 molar. There's your calculation formula. The nitrate is 0.10 molar. But the aluminum concentration here is 1/3 of the nitrate concentration. I hope you see that from the equation for the dissociation of the salt. Therefore, the aluminum concentration is 0.1 molar divided by 3, or 0.033 molar. And when you look at that, you may have put that down and got a wrong answer. That's a programming mistake on the quiz, because this answer is correct and it was incorrectly marked wrong. If you have any questions, please consult your teacher, and I hope you have learned something from this.